Okay, well, good morning, welcome everybody. I'm very happy to present this Andreas Quirrenbach today, that he can give a seminar during his visit this week. Well, usually we start this introduction by a brief bio of the speaker, but this would maybe take a little bit too long in this case. So, well, just saying, he's held a lot of positions in the past. He's both in Europe and in the US. I think I just heard you did a PhD in Bonn, but you were in Washington. You had a position in San Diego. You worked with Reinhold Jensen in Garching, where he actually developed, I just learned, the first laser guide system in Europe, which is still at the basis of what they're using now in Paranal. So. He was also at the root of interferometry in Europe, I believe. So he's been doing a lot of things. You are also working in Leiden. But now you're not going to talk about instrumentation, not about the interferometry or the AO, but about terrestrial planets orbiting low-mass stars.
Okay, thank you very much. Yeah, thank you very much for the nice introduction. And thanks for your hospitality. It's really great to be here. I enjoyed yesterday a lot, and I'm enjoying today a lot. So I will talk about small planets orbiting small stars, but of course also a little bit on instrumentation to do that. So to start, let's just quickly recall the methods that we use to detect extrasolar planets indirectly. One method that is fairly well known, also it garnered a Nobel Prize for Michel Mayor and Didier Queloz. That's the radial velocity method, where we look for the motion of the star around the common center of mass. So the principle is very simple. The star and the planet move around the common center of mass. The difficulty is that the star, say, take the example of the Sun and the Earth. The Sun is 300,000 times more massive than the Earth. The velocity of the Earth is about 30 kilometers per second in its orbit around the common center of mass. The velocity of the Sun is 300,000 times smaller, which is 10 centimeters per second. So here we have to detect very small changes in the radial velocity corresponding to very small changes of the Doppler shift of spectral lines. And importantly, the observable that we get out of that, provided that we know the mass of the star, which normally we do for main sequence stars with sufficient precision, provided we know that, the observable is the mass of the planet times the sine of the inclination angle. But importantly, the mass of the planet appears here. The other very well-known detection method that has been very successful is transit photometry. Here you take advantage of the geometry if the observer is nearly in the plane of in the orbital plane of the planet moves in front of the star and behind the star, and then you get, when it is in front of the star, it blocks some light from the star, you get the transit. And if it disappears behind, you get what is sometimes called the secondary transit or the eclipse, where you don't get any light from the planet. Also here, notable, what are the observables? So here, when the planet goes in front of the star, you can measure the depth of the transit, and that tells you the radius of the planet. So here, the primary observable is the radius. Also, you can use the transit to do spectroscopy by looking at the atmospheric transmission. If you have a gas in the atmosphere that blocks light from the star, the radius of the planet appears a little bit bigger. It's the surface plus the atmosphere that's absorbing light from the star. If the atmosphere is transparent, the planet looks a little bit smaller. So you get variations of the transit depth with wavelength that you can translate into a spectrum of the planet during the transit. And finally, during the eclipse, you block light from the planet, And if you do that in the infrared, this gives you the day-side temperature of the planet. So this is, looking at the eclipse is a way to get information about the temperature. And I come back to that because that comes back into play later on. So it's important to note that different methods give different types of information on the planet. So, and then if you combine these observables, if you do follow-up, for instance, of transits with the radial velocity method, you can get the mass and the radius, and that gives you the density and the surface gravity. So again, there is a high value in combining different techniques. First of all, for confirmation that it's really a planet that you are looking at and not some artifact, but also the combination of these parameters then gives you physical insight that you can't get from one method alone. So we have been trying to do that, but there are complications for combining transits and radial velocities. You can't just go and look at a catalog of detections or candidates from one technique and say, no, I'll do the other technique and get the complementary information for all of them. First of all, not all planets transit as viewed from the Earth, because you have to be nearly in the equatorial plane of the orbit. If you aren't, you get any occultations or transits. So, and the probability is the radius of the star divided by the distance of the planet from the star. So for the Earth, this is about 0.5%. So out of 200 random observers in the universe, one sees the Earth transiting the sun. So, or in other words, if you do a transit survey, for each planet that you see, there may be dozens or hundreds that you can't see because the geometry is not right. Then also precise radial velocities are possible only for bright stars. And the star has to have sharp absorption lines. So that means there are quite severe magnitude limits. And these are typically depending on exactly how precisely you measure, how big your telescope is, how patient you are. The magnitude limit of radial velocity studies are typically between 6 and 12 magnitude. So transits from some of the space missions can occur around much fainter stars than these limits. And it's just technically not possible with a 8 or 10 meter telescope, and even less with a smaller telescope, to get sufficiently precise radial velocities to measure the masses. And it's restricted to spectral types of F, G, K, and M, so earlier type stars do not have a sufficient number and sufficiently sharp absorption lines to do good radial velocities. And so there are the typical strategy, if you want this combined type of information, is you do radial velocity follow-up of transit candidates from space missions. So we have had some space missions that have done large surveys, and there is a trade-off in these missions, a trade-off between the survey area and the duration for which the mission looks at a given field. So, for instance, in the ones that have delivered most so far are Kepler and TESS. Kepler had a quote-unquote small field of view. It was designed to have a large field of view, so it was the largest that was technically feasible. Still, it's a small fraction of the sky, but it looked at a field for several years. So it saw lots of planets that have relatively long orbital periods, up to a year or so, but only in a restricted area of the sky. And a restricted area of the sky also means that the average brightness of the targets was were relatively faint. There were many other very bright stars that it never observed. TESS was or is the opposite part of the parameter space, trying to do the whole sky, but then only for about 4 weeks in each field, and then it moves on to the next field to be able to cover the full sky. So you get all the bright targets, but you don't get periods that are very long because it doesn't look for a very long time. And the upcoming European Plato mission is somewhat in between, so a larger field than Kepler, but not quite as large as TESS, fainter targets than Kepler, but not all the bright targets that TESS gives. So this is kind of the trade-off in the mission design, and therefore there are different types of opportunities also for ground-based follow-up. So now I would like to talk mostly about M-stars, the low-mass stars, and there's specific opportunity. So first of all, one has to realize when I talk about M-stars, it's a huge mass range that is called an M-star. The M spectral type covers a range from about 0.08 solar masses, which is the hydrogen burning limit, to about 0.6 solar masses. So if you look at this on a logarithmic scale, which is kind of the relevant parameter or the relevant way of looking at it, the M spectral type covers more range in log mass than A, F, G, and K together. So an early M star, one with at the higher end of the mass range, is very different from a late M star. So that's the first thing to note. And having this large mass range, if you do say a survey of M dwarfs, allows you to test planet formation scenarios because these stars are so different and have different protoplanetary disks. You can really use observations of M stars to test planet formation scenarios. Also, detecting and characterizing terrestrial planets is much easier for M dwarfs than for F, G, or K stars. So first of all, the transit depth depends on the radius of the planet divided by the radius of the star squared. And so this is typically 10 to the minus 4 for a G star and an Earth-like planet. So therefore you have to really go to space and build missions like Kepler and Plato, whereas for a late M star, this ratio is only 1%, so you can do it from the ground. Or you can do it from space much easier. Also, the radial velocity signal scales with 1 divided by the root of the mass of the star. And typically the systems that around M dwarfs are more compact than those around G-type stars. So there's also the scaling here with the size of the system to minus 1/2 power. So to find terrestrial planets around G stars, the required radial velocity precision is about 10 centimeters per second, but 1 meter per second, an order of magnitude less stringent for a late M star. So the next point is the habitable zones of M stars. So the term habitable zone is frequently used in a very loose way in just saying that I'm looking at the distance from the star where I get a temperature that is suitable for liquid surface water. And for M stars, they are close to the star, which means the typical orbital periods of the order of 10 to 30 days. And this is also very good for the detection with transits or radial velocities. First of all, the signal is bigger, as I just explained, but also it's much easier to do from the ground, for instance. If you look at the habitable zone of a G-type star, which by definition is about 1 year, you get in all kinds of telescope scheduling problems with your annual cycle of when a star is observable or not. Whereas here, within one observing season, you can cover several orbital periods and find a planet in the habitable zone of an M dwarf, but just by looking for 3 months, you are covering several orbits. But then if you think about the term habitable zone as signifying something that really has to do whether this is a habitable planet in the sense that maybe there's life on it, or life could develop on it, then you have to enter other considerations, namely, can it sustain an atmosphere? And then there's these planets around M stars have a much higher ratio of extreme ultraviolet flux to bolometric flux. That means for a given temperature, they are blasted a lot more by UV radiation that may erode the atmospheres. Also, the star has a long lifetime as a young active star, which means also the time over which the atmosphere could erode is much longer. There are many unknowns. In principle, one would have to know the UV emission over the full lifetime of the star to really assess whether the planet could be habitable or not. And also we don't know that much about outgassing that might play a role. So my take on it is currently these systems are very interesting, first of all, to find them, to characterize them in their bulk properties, and then they will provide examples that are different from the Earth for further study of things that are more related to real suitability for biology. So we started a project to look for these type of objects, and we called it Quirrenbach. So this is the acronym, which is also the summary slide of the talk. The acronym has it all. We built an instrument for the Cala Alto Observatory. We do high-resolution spectroscopy. We target M-dwarfs. We are interested in exo-Earths. We are in the near-infrared and the optical, and technically what we build are Echelle spectrographs. And Quirrenbach is Spanish. It means gardens, and it's a nice acronym because it's easy to Google. It's not like some other acronyms that are nice, but that have many other meanings, and you get confused with other search results. If you search Quirrenbach, you find us. It's a consortium of 10 institutions in Spain and in Germany, because Cala Alto was a German-Spanish observatory at the time we started. And so we asked the questions, what kind of instrument should we build if we want to look for these objects? So the first thing to look at is the spectral energy distribution of an M-type star. So this is a typical M-star spectrum. And the instruments that existed when we started to think about this, this was around 2010. The instrument that existed, they were observing in this spectral range here. HARPS, for instance, the longest wavelength that the HARPS spectrograph covers is 630 nanometers, somewhere down here. And clearly, this is not really what you want if you are interested in M-dwarfs. You really would want an instrument that is here in the near-infrared. And so therefore, we decided to build an instrument that covers this wavelength range. And you note that here is 1,000 nanometers, 1 micron. So this is kind of the boundary technically between what can be done with silicon-based detectors and where you have to go to near-infrared detectors and different technologies. So we decided to build 2 instruments, one covering this range here and one covering that range. So we have a visible spectrograph, but red optimized in the red part of the visible and a near-infrared instrument. So the overall instrument layout on one view graph is like this. We have a front end. So this is the optics that attaches to the telescope. We are at the Cassegrain of the 3.5 meter. The light from the telescope enters here, and there's a dichroic beam splitter that splits the visible light from the near-infrared light. The visible light is sent into a fiber to the visible spectrograph. The near-infrared light goes the other way. There's calibration light that is also injected here from calibration units that are also coupled with fibers. And there are all kinds of auxiliary things. So the core of the instrument are these 2 spectrographs that are in vacuum. And so they look very similar from the outside. They're also very similar on the inside, except that one works in the visible with a visible light detector, the other one in the near-infrared. And here's a picture of the telescope. So altogether, we cover the wavelength range from a little more than half a micron to 1.7 micron. We have a spectral resolution of 90,000 or 80,000 in vacuum. Temperature very nicely controlled at the millikelvin level. And here we have a 4,000 by 4,000 pixel CCD. And here in the near-infrared, we have 2 detectors that have 2,000 by 2,000 pixels each. So this is an illustration of, or actually these are actual data, but a little bit artificial color put on them to make them look a little more interesting, of one readout that we get. So to explain this, the spectrographs are what are called cross-dispersed Echelle spectrographs. An Echelle spectrograph is a spectrograph that works at a high spectral order. Yeah, you know, when you have a grating, you have the first diffraction order, the second diffraction order, the third diffraction order. In an shell spectrograph, you typically use the orders, say, 80 or 100 or 120 or something like that. And then if you look at the grating equation, or if you want to find out where you get a spectral line, you ask the question, I look at the wave that is reflected by one groove on your grating and the one that is reflected by the next groove of the grating. You calculate the path length difference, and if the path length difference is an integer multiple of the wavelength, you get constructive interference. And that's the condition for getting a line in a certain direction from a grating. And let's say you calculate this difference and it turns out to be 50.5 microns. If the difference is 50.5 microns, then you know that this is 100 times 505 nanometers. So in this direction, you get light from 505 nanometers. It's also 101 times 500 nanometers. Yeah, so in the same direction, you get light from at 500 nanometers and at 505 nanometers. One in the 100th order and the other one in the 101st order. Yeah, and then you have to sort this out. You take a prism or a grism at 90 degrees from your grating, and that disperses the light in the other direction. So that separates. The 100th order is here, and the 101st order is here, and the 102nd order is here. And so this is a cross-dispersed shell, so you have the shell dispersing in one direction and the cross-disperser dispersing in the other direction. So you see that in this picture here. You have the lower orders up here in the infrared, and these are higher and higher order numbers down to the blue. So down here you have something like the 130th order, and up here you have the 70th order, and each line here is one of these orders. And this zooms into one of these orders, and here you have a stellar spectrum. So this is a star, and you see stellar lines here, and it looks a little bit funny, and so you see two streaks, and the reason is that we have what is called an image slicer in it. So the image of a star is round, and we take an optics that cuts it in the center and takes the two half moons and puts them up like this. And this gives you twice the resolution of the spectrograph without having to make it bigger. Yeah, so this is a trick to make instruments of a manageable size and a high spectral resolution, is to put in this image slicer, and therefore you get two streaks here for the star. And this is light from a Fabry-Perot etalon that has very regularly spaced lines. So this is the calibration light from our etalon. This is the starlight, and a planet will now move these lines back and forth as the Doppler shift changes. So the task is to measure changes of the position of these lines of the star with respect to these lines of the calibration source. And 1 meter per second, which is the precision that we reach, corresponds to 1,000th of a pixel, or about 10 silicon atoms on the chip. Yeah? So our signal is when these lines move by 10 silicon atoms, then we have a planet of an Earth mass, roughly. And actually, it's much more complicated than that, because the Earth also moves. So the whole spectrum moves by 30 kilometers per second, or up to 30 kilometers per second back and forth, because the Earth moves in the course of a year. So in reality, we don't get a nice 10 centimeter per second signal, but we get a 30 kilometer per second annual signal and a small modulation of 10 centimeter per second on top of that. So that's the instrumental challenge in building these instruments. The principle is simple, but you have to get to be able to reach very, very high precision here. Yeah, so I mentioned that we built 2 instruments, and one reason for that was that we didn't really know at the time which wavelength band was the best. So it's pretty clear that the cooler your star is, the more the spectrum shifts to the red. So if you have a range of spectral types, you expect that for the earlier spectral times, for the warmer stars, the visible spectrograph would be better, and for the really cool stars, the infrared spectrograph would be better because there's more infrared light for the cooler stars. And at some point, the sensitivity or the precision of the 2 should cross over, and we expected that this crossover would be somewhere at spectral type M3. And we were surprised to see that this was not the case. The crossover is more like at M6 or something like that. And the reason is that what counts is not only how much light you get, but also how much information that light carries. And the information that the light carries depends on the number of spectral lines. And when we went to the telescope with our instrument, we saw that this range here, where we had expected lots of lines from iron hydride, these lines were shallower than the models had predicted. Observed spectra didn't really exist at the time. We had to rely on models, and the models over-predicted Fe over H, iron hydride, the depth of the lines in this range. So our precision was a little bit worse than we had expected. So these are the data for each order of the spectrograph. These are bins of these data, and this is a bin over the whole spectrograph. So this was higher than we had expected because the lines were not as deep. On the other hand, in this range here, you have titanium oxide bands. So the bands that really define what an M-dwarf is strong titanium oxide bands, and they turned out to be better for our radial velocity measurements than we had estimated. So here we get higher precision. So down is better, of course, smaller errors. So this is better, and therefore, in the end, it turned out that for almost all of the stars we could observe, the data from our visible light spectrograph are more precise than from our near-infrared spectrograph. That was the first thing we learned. Nevertheless, it's very useful to have a wide wavelength range because a wide wavelength range gives you a handle on what the star itself does. For instance, if the star has a spot, you get a modulation of the radial velocity that you observe. So if you have a spot on the star, and the star is rotating, the spot appears on one side of the star and it rotates across the surface, and it blocks some light. And first it blocks some light that is blue shifted because it's coming towards you on that part of the stellar surface, and then it blocks some light that is red shifted, so you get a radial velocity signal that is first positive. So it's this one here. First, the flux blocking signal first blue shifted and then red shifted. Also, there's convective blue shift on the surface of the star. There's convection cells, and the material that's coming towards you is hotter because it comes from the interior of the star. So that is blue shifted, and that gives a net blue shift. And the spot is associated with a magnetic field that blocks some of that turbulent convection, and therefore it blocks some of the blue, or it reduces the blue shift, so this gives a red shifted signal. And so you get a combined signal that has an interesting shape, and this shifts the center of lines, and this can this modulates the radial velocity with a period that is the rotation period of the star. And this signal typically is stronger in the blue than in the red because all these temperature effects play a larger role in the blue. So having 2 spectrographs and having a wide wavelength range helps to distinguish this type of stuff from real planets that pull on the star with effects that are totally wavelength independent. Okay, so we selected stars for our survey, and we did this in a way to cover the whole M spectral range as uniformly as we could. And here, the late spectral types, these are the really low mass stars. Those are really nice. We tried to do all of them that we could. So these are all the stars that are in so in the spectral types M5.5 to M9 that are bright enough for us to observe reasonably well in half an hour. There are just not that many in the sky that can be done with a 3.5 meter telescope. And here we try to be as uniform as possible, and the average distance in our sample is 13 parsecs. So we're really looking at the solar neighborhood. The planets that we are finding are really close, much closer than any other survey is doing, much closer than the typical transiting planets and so on. So our goal was to find planets in this mass range down to about 1 Earth mass. And yes, we found some. So here is Teegarden star, which has a mass of a little less than 1/10 of a solar mass. And here's a periodogram where we test whether there's a periodicity in our radial velocities. We see 2 big peaks here at 4.9 days, at 11.4 days. And yes, these are 2 planets orbiting Teegarden star. And here are the parameters of them. They have masses that are really very close to 1 Earth mass. And also their insolation is very similar to the Earth. So they are at a temperature that is not so different from the Earth, and they have a mass that's not so different from the Earth. And there are different ways of defining similarity between planets. By some measure, these are the planets that are most similar to the Earth amongst all planets that are known. But of course, the parent star is very, very different from the Sun. So you can put this in a diagram where here you put the insolation, how much energy do I receive versus the stellar effective temperature. Here's the Earth with the effective temperature of the Sun, and of course 1 in insolation. And here are those 2 planets, and here actually this is for 2 different analyses of the stellar spectrum about the stellar properties. So this was our initial goal, and here we can say, well, goal of the project, we achieved it. We found the planets that we were looking for. Now, of course, we want to do a bit more than that, and recently we finished an analysis about all the stars in our sample that have masses less than 0.16 solar masses. So these are the really low mass stars between the hydrogen burning limit and 0.16. And in this plot here, we have a plane in which we have the period of the planet and the mass of the planet. And these points here are all planets that we found, or that are there in our sample. And so the first point to note is we looked at 15 stars, and there are 11 planets. So that means there are a lot of them. It's not just occasionally one, but typically these stars do have planets. So I should also say the background here is an analysis of our detection probability. So we performed injection retrieval tests and see how, if there is a planet with these characteristics, a certain mass, a certain period, how likely is it that we find it? So black means we have no chance. Light yellow means we find all of them. And somewhere here's the transition. So then we can look at this diagram a little more carefully and learn something about the distribution of these planets in this plane. So this is a log plot, log period, log mass. So frequently when people model planet populations, they assume log uniform distributions. You have the same number of planets between 1 and 10 Earth masses as you have between 10 and 100. and you have the same number of planets orbiting between 1 and 10 days as you have between 10 and 100. So if you make this kind of zero, no prior knowledge assumption about the planet distribution, they would be uniformly distributed in this plane, because it's a log-log plot. And the actual detections would then be uniform multiplied by the background color. And this is clearly not the case. Yeah, you can see this is maybe the case in the horizontal axis. So it's kind of compatible with having a log uniform distribution in period, but it's clearly not compatible on the vertical axis. So we learn we have very few planets here that are more massive than about, say, 1 or 2 Earth masses, and we have a lot down here at about 1 Earth mass. So we have a very steep mass function around these very light stars that sets in at around 1 Earth mass. And one very interesting question that I have been discussing with colleagues lately is, well, what does this actually mean? It could mean that what we see here is kind of the massive tail of a distribution that extends down here by quite a lot. And we just see the most massive examples of planets that are typically, or a large population that is lighter than that. It could also mean that there is a typical planet mass of around 1 Earth mass. And some of the planet formation people say, maybe we expect that these low mass stars typically have planets that have 1 Earth mass. And you really have to have the sensitivity to go down to 1 Earth mass. If your instrument can only see 2 Earth masses, you will miss all of these planets. So that's a very nice statistical result. So here is a table where we computed incidence numbers. So between about half and 3 Earth masses, we say statistically we see about 1 planet between 1 and 10 days and 1 planet between 10 and 100. So in total, you have about 2 planets in this around this 1 Earth mass for each one of these low mass stars. So we also saw multiple systems. For instance, in this low mass star, which is also not much more, I think it's 0.12 solar masses, we see 3 planets with periods of 2 days, 3 days, and 4.5 days. So these planets form what is called a resonant chain. This is 2 to 3, and this is also 2 to 3 in period ratio. So the system would not be stable if these planets were not in this orbital resonance. And now you can ask the interesting question, what about, statistically again, about systems with multiple planets around these low mass stars. So this is for up to 0.2 solar masses, and here are multiple systems. Here's the very famous TRAPPIST-1 system, known, that is very well characterized because it happens to be a transiting system. And all these planets here form such resonant chains. Here's our YZ city example, which is also a resonant chain. And so here, this is over the x-axis I have period. And here I renormalized the periods to what is called the mutual Hill radius. So that distance has a scaling in it with the mass of the planets and the mass of the star that tells you about the stability. And typically, systems need to have a mutual Hill distance between adjacent planets of at least 12 or 13 or so to be stable. If the distance is smaller, the planets interact too much and they kick each other out of the system. And you see that most of the systems are on the right here at larger mutual Hill radii. TRAPPIST-1 is inside and YZ city is inside. So that is, again, tells you about the importance of resonances. And then we found a 3rd planet in Teegarden star, and the system is still outside. So we found a 3rd one. But radial velocities have one disadvantage over transits. In transits, you get all the planets essentially in the system. They do transit rather quickly. If you do radial velocities, you have to work for a long time. So this TRAPPIST system, now we have, I think, 400 spectra, each spectrum taking 20 minutes of integration time. It's an enormous amount of telescope time that went into the system because the signals accumulate over long time. And we have indications that there are more planets probably in the system. And you can play a little bit with the residuals in our data. It is plausible that there are 2 additional planets that would make also a resonant chain out of the Teegarden system, and then it would look like this and be again inside and here. So some people have been claiming that TRAPPIST-1 is a very unusual system. I don't think this is the case. I think TRAPPIST-1 is a rather typical system, probably. The only thing that is unusual is that the Earth happens to be almost in the orbital plane and we see it transiting. If we had other similar systems where we happened to be almost in the orbital plane, we would also see many planets and we would see other systems that are also resonant systems. So take-home messages number 1, almost all of these low-mass stars have terrestrial planets with a very steep mass functions. Multiple systems are rather common and probably even resonances. So if you look at what we have been doing, here is a diagram that has the stellar mass and the planet mass. And the red and blue are all from our Carmenes instrument. You see we have done quite a bit of work and populated this low mass part of this diagram. And I've talked mostly about these planets, low masses here. There are also some, not many, but a few that appear up here. So these are high mass planets on these low mass stars. And here's an example of one that has actually 2 such high mass planets. So this is a star GJ3512, again with a low mass, that has 2 planets with masses of half a Jupiter or so. And this is interesting because it's a real challenge for planet formation theories. So here are diagrams that simulated planet formation around low mass stars. So it goes down, this is stars with a half a solar mass, with 0.3 solar masses, 0.1 solar mass. So you have generate synthetically planets around these systems, and they form a big cloud here, and the planets that we detect, these planets are up here. So very far from what these planet formation models actually produce. So this is a real challenge to understand what these planets are, how they form, and it's quite possible that they form through a different mechanism than these terrestrial planets further in. Maybe they are made by direct collapse of the protoplanetary disk rather than by core accretion. So take-home message number 2, Jovian planets around low-mass stars are not common, but they do exist, and they are a real challenge for standard planet formation models. So now coming back to densities, putting together the information from mass and radius, now we can of course construct a mass radius diagram and plot the planets, and there are many versions of this. And I find this really impressive. I hadn't expected several years ago that we could draw such a diagram that extends down to 1 Earth mass and less. So a few of these for instance, are the TRAPPIST-1 planets, but all the others are radial velocity planets coming from instruments such as Carmenes and others like Espresso and HOPS working in the southern hemisphere and so on. And here are compositional models. So this is what a 100% ion planet would look like in this diagram of mass radius. The red one would be pure silicate composition. The green line here is the composition of the Earth with an ion core and a rocky mantle. And one can see that, well, first of all, this is clearly incompatible with our composition. So we can say these planets are not like completely ion or a composition with a very heavy core like Mercury. And there is at least an inkling that the data are more compatible with an Earth-like composition than with them being pure silicates. So here the error bars, we should try to get smaller error bars by follow-up observations. But we are now at the point where we can not only find these planets, we can measure their densities well enough to make meaningful statements about their mean densities, compare them to different interior compositions. And if you make the additional assumptions that planets are kind of composition like the Earth with a metal core and a silicate mantle, we could transform this into a diagram where we say for each planet, what is the core fraction of the planet, and would conclude, well, it's not so different from the core fraction of the Earth. So we can now measure densities with about 20% precision down to 1 Earth mass, and most of these planets that are smaller than about 3 Earth masses have an Earth-like composition. So that's the other conclusion here. There are few outliers here, but down here, almost all planets follow one kind of model, whereas then up here, at larger than 3 Earth masses, now you start seeing much bigger planets that have thinner outer envelopes. And those don't occur apparently, though we have to look into more detail into these outliers here, why they appear here. But almost all of these planets are down here where at least if there's any atmosphere, it must be very small. And so that gets back at the question, what about atmospheres? What about habitability? What about being able to hold on to an atmosphere? And here we have some Kamenes data that are interesting in this context, and this is about flares. So if you have a planet that is irradiated, you have a lot of UV photons on the atmosphere that can drive off the atmosphere. You may also have coronal mass ejections from the star, so particles impinging on the atmosphere and eroding the atmosphere. And interestingly enough, we know a lot about coronal mass ejections on the sun, and we hear about that in the news, because coronal mass ejections can disturb our satellite communications, kill astronauts, cause power shutdowns, and so on. So they have real implications for us on the Earth. So we know a lot about these things on the sun, and we know very, very little about coronal mass ejections on other stars. There are less than half a dozen papers in the literature that have halfway convincing demonstrations that coronal mass ejections appeared actually on another star than the sun. We know a lot about flares, but we don't know how many of them are associated with coronal mass ejections. And that's important in the context of habitability. So what we did here is we scheduled Kamenes observations of this star while it was also being observed with TESS. So we knew that the TESS observations were going on. Of course, we didn't know what TESS was seeing because they download the data a couple of weeks later. So we just knew it was observing, and we scheduled a few spectra to be taken during that time. Here is the TESS light curve. So this modulation here is the rotation of the star, which is heavily spotted. And every once in a while, you see a big blip here. And these are not problems with the data. These are all flares on the star. And so here we have a very, very strong flare. The star got brighter by a factor of 1.7. And this is white light observed by TESS. Yeah, imagine you had a solar flare and the sun would all of a sudden be twice as bright as it usually is. So this is a huge flare. And one of our spectra was taken a few hours later. And here are the spectra. And this spectrum is different from all the others in that it has a very, very large blue wing in the H-alpha line. And the blue wing in the H-alpha line means there must be material that is coming towards you, and quite a bit of material. So we think that this spectrum shows that this flare ejected material that is visible in H-alpha even hours after the peak of the flare. And that's very unexpected, because normally such changes in the line shape last only 4 minutes or so. So this is something that has nothing similar in the literature. We have to see whether we can repeat similar observations and learn more about what is happening with the atmospheres of these stars. So in a completely different direction, there's now also a large program that's being carried out with JWST and HST that looks at the question whether these planets may have atmospheres. And this was pioneered by Laura Quirrenbach and others taking Spitzer observations of a secondary eclipse. So that brings me back to what can we learn from transit observations. From infrared observations of the secondary eclipse, we can infer the daytime temperature of the planet. Yeah? So here is the light curve, here is the secondary eclipse, and the depth here tells you what the daytime temperature of the planet is. And in this diagram, this shows theoretical models that try to relate the daytime temperature to the presence of an atmosphere. If you have a high pressure atmosphere, it will take away heat and distribute it from the day side to the night side. Yeah? Think about the difference between the Earth and the Moon. The Moon has a much higher contrast between day side and night side because there's no atmosphere transporting heat from the day side to the night side. On the Earth, the day side night side difference is much less, and the day side therefore is quite a bit cooler than the day side of the Moon. And so this is the same idea here. And if you put models on with a higher and higher surface pressure, then the day side temperature gets lower and lower, and therefore the depth of the eclipse gets smaller and smaller. So from the depth of the eclipse, you can learn whether the planet has an atmosphere or not. And this is now being pursued in a big program in a systematic way by JWST. And so the parameters that influence whether a planet can hold on to the atmosphere or not are the escape velocity from the surface of the planet. So the higher the escape velocity, the more difficult it is for an atom to leave the planet. And that means to the right, it's more likely that the planet has an atmosphere. And also, of course, if you have higher insolation, higher flux impinging on the planet, that makes it more likely for the atmosphere to be evaporated. So if you plot a diagram in these two parameters and plot all the planets that we have around M dwarfs, you expect that to the bottom right, it's more likely to have atmospheres, to the top right, less likely, and the dividing line between having or not having atmospheres, this is frequently called the cosmic shoreline. So if you have heard the term cosmic shoreline, you may have thought about beaches and palm trees. It's actually the question, does a planet have an atmosphere? Can it hold on to an atmosphere or not in such a diagram? And so JWST is now targeting planets selected here. It has observed one planet so far, actually one that was the discovery paper was a Kamenes paper led by one of my graduate students, so it's nice to see that we actually have an impact also on what JWST is doing, providing targets to them, and they now want to map this, and this is clearly something very interesting to watch because it can tell us now whether these are bare rocks or whether perhaps those more to the bottom right really do have atmospheres. It doesn't tell us then what the composition is, but it's a first step to finding atmospheres. So to conclude, at the present state of the art, transit missions and radial velocity spectrographs can find planets that have about 1 Earth radius and 1 Earth mass if we look around low mass stars. So the big thing for the future for missions like Plato from the European Space Agency as a transit mission, and then further in the future, Habitable Worlds Observatory, they are aiming at extending this to sun-mass stars. But it can be done today for low-mass stars. We know that there are about two such planets, one Earth-mass planets per star in this for these low-mass stars. The densities are consistent, at least, with Earth-like composition. A fair number of them may be in closely packed resonance systems, similar to TRAPPIST-1, which may be quite typical. And we may soon find out whether they have atmospheres. There are also Jovian planets around these stars that are very challenging for formation models. So it's a very interesting field, and we hope that we can continue with our spectrograph, and that, of course, the other missions will find out a lot more about these planets around low-mass stars. So thanks for your attention.
Thank you very much, Andreas, for a very interesting talk. We have time for a couple of questions. Are there any in the room? Yeah, Shreya?
Hello. Thank you for the super nice talk. I have two questions, if I may. The first one is, so we are talking about M dwarfs, of course, low mass stars, but also cool, full of molecules. You mentioned that the TIO bands help you actually for getting better precision, RV precision in optical. But I was wondering, of course, your RV detection, the planet detection, the precision is not hampered by them. But when it comes to characterization of your planets, planet atmospheres, etc., do these molecules give you a challenge, a problem in doing so?
That's a good question. Yeah, the M dwarfs are challenging. It's partly the complexity of the atmosphere. So in the radio velocity analysis, we have to use different methods from those that are used for the analysis of G-stars, which frequently compare the stellar spectrum to a theoretical line list. And our spectra are so complicated we can't do that. So we have to use different methods. We form empirical templates by averaging our observations, because it's impossible to predict the spectra from theoretical models. So this is one complication in the analysis. Also, the M dwarfs are quite active. So we have quite a bit of what is called jitter in the radio velocities from activity flares and so on. So we have to take a lot of data to kind of average over this floor. So some other stars, probably early K stars, are quieter than our M stars. And there are quite a few stars that are just not suitable because they are still rapid rotators and so on.
Yeah, actually my second question was related to the RV jitter, but yeah, you explained it. So the jitter that you, of course, have already great precision, so congratulations on that, but there was still some jitter, and indeed, I guess it's...
Yes, so we are basically at the point where it doesn't pay off very much anymore to improve on the spectrograph, because we are limited by the stability of the star itself, which is typically of the order of 2 meters per second or something like that. So all we can do is then take dozens or hundreds of spectra to average over this intrinsic jitter of the star that is very, very difficult to model. And we knew about that, of course, before, and that was one of the reasons why we designed it to have this large wavelength range, and we include an analysis of H alpha and other lines that give us some indication of intrinsic radio velocity shifts and so on.
Indeed. Thank you.
Time for maybe one more question. Janis?
Thank you a lot, Andreas, for your very nice presentation. I had a hopefully quick technical question that I think I didn't understand something, and then a more general one. So you compared the Carmenes HARPS post and HARPS pre-data, RV data, to find the tertiary planet. You had the slide, I don't remember the number, but the HARPS pre-noise was about half HARPS post, and I didn't understand how you had... I'm guessing that's post-processing.
Yeah. No. HARPS pre and post is there wasn't a technical intervention.
Sorry.
And
so that's
so
what I didn't-
typically when you look at archival data from HARPS, you split them into two because there's a big jump
I was
between
not aware of that.
before or after they did this technical intervention at HARPS.
Okay.
So pre and post is always
Yeah.
separate in time.
Yeah, thanks. And the general question I had, so you mentioned that the atmospheric band information for M dwarfs, or the models that you built your expected performance on, overestimated the depth of the lines in the atmospheric band that you wanted to use. What has happened with that? Like, I mean, what was the follow-up? Have these models since then been improved? Has there been some feedback to the, let's say, atmospheric modeling community? Can we use more up-to-date models to, make sure we don't duplicate the kind of shortcoming?
That's a very good question. And actually, I have to confess, I don't really know the answer. We actually, was one of our first things we did was we published one spectrum for each of the stars in our sample so that people can do exactly that. And I haven't followed up really whether this has entered or how this has entered into modeling. I know that these data have been used by a number of groups, but I don't know specifically whether they have looked at models for, say, iron hydride and modified what was known before. I don't know.
Okay, I think unfortunately we probably have run out of time for questions, but Andreas will be here for the rest of the day, so if you go and grab him for more questions. And if you'd like to thank Andreas again for a lovely talk. Thank you very much for coming. The next seminar will be on the 18th of September.